The present video is part 2 of analog communications dealing with angle modulated systems. Let us summarize the contents of this video here. We know that continuous modulation schemes are divided into two categories: linear modulation, that contains the AM systems, amplitude modulated systems, and non-linear modulation, under which the angle modulated systems come. In angle modulation, phase or frequency is changed according to the message signal. Angle modulation results in infinite bandwidth. Fortunately, most of the energy is contained in finite bandwidth. Bandwidth in frequency modulated systems is estimated using Carson's rule, that is, bandwidth is sum of twice peak frequency deviation plus twice the message bandwidth. Wideband frequency modulated signals can be generated by narrowband FM signals and frequency multiplication or by direct methods. Demodulation can be done by using discriminator or by phase lock loop. Wideband angle modulated systems provide improvement in output signal to noise ratio over linear modulation schemes, and this part will be discussed in the next video, that is part 3 on noise. Now let's start our video presentation here. This is we start with the angle modulated systems. Here angle of the carrier is changed in accordance with the instantaneous amplitude of the modulating signal. There are two types of such modulation schemes available. One is frequency modulation and the other is phase modulation. So this part of video will talk about these two schemes here and try to summarize the important observations which are related to these modulation schemes. This kind of modulation systems, that is frequency and phase modulations, provide certain uses like for commercial radio broadcasting. They are being found very useful, and they could be used for like a good quality music reception. So for entertainment entertainment kind of broadcastings, they are quite useful. Sound transmission in television, that means the sound transmission of television is in FM, frequency modulated, while the picture is amplitude modulated. Now the third application is two-way mobile radio. This application is related to phase modulation schemes because these schemes are useful for having a two-way mobile radio. Now the last application, microwave and satellite communication, these frequency modulation schemes are very common. Now advantages over AM. We are trying to find what are the advantages over the linear modulation schemes for these modulation schemes. First is freedom from interference, since AM is noisy than FM. We have observed that the interference due to noise and the neighboring channels is considerably reduced in case of frequency modulation. So that's why we say that AM is more noisy, but the cost of these systems is definitely high. Now notice here they operate in VHF band. This is a typical VHF band considered 88 MHz to 108 MHz and provide high degree of fidelity. That means you can receive the signal with good fidelity, good reproduction. This picture here shows the various waveforms, like we notice here this like a carrier waveform. It's a sinusoidal modulating signal. You can notice here that this carrier waveform is having a high frequency, while the modulating signal is a relatively low frequency signal. And this waveform is corresponding to amplitude modulated systems. And here the other modulation schemes which we are going to discuss in this part is phase modulated signals. You can notice here this is the waveform for the phase modulated signal. We notice the amplitude remains constant, only the corresponding phase or frequency of the waveform is being changed. And you see frequency modulated signal, if you notice here the signal is having higher frequency when its amplitude is modulating signal amplitude is higher, and it is having the lowest frequency when this amplitude is the lowest. But it is not easily distinguishable in the case of tone modulation, whether it's a amplitude modulate, whether it's a phase modulated signal or frequency modulated signal. Now we start with the angle modulated signal. Here in this approach we have tried to give a unified analysis of the phase modulation and the frequency modulation kind of modulations. We notice here in this angle modulation is a, we said, nonlinear process, and here we note AC is the amplitude part of the carrier and omega CT is the angular frequency. These are constants initially, but they vary with the modulating signal. We can also call this modulation exponential modulation. Sometimes we call it exponential modulation. Now this modulated signal, which is A cos omega CT plus phi t, can also be represented in exponential form, real part of AC exponential j omega CT plus j phi t. Now from this we can define the instantaneous phase, that is theta it, could be defined at omega CT plus phi t, giving the instantaneous phase, that's omega CT plus phi t, and instantaneous frequency, you take a differential of this on either side. This omega it would be d theta I over dt, that would be omega c plus d phi over dt. function phi t and d phi by dt are referred to as instantaneous phase and frequency deviations. We notice here for phase modulation, the instantaneous phase deviation of the carrier is proportional to the message signal here. That phi t phase deviation is proportional to the message signal, and kp is phase deviation constant, that's radians per volt. Okay. Now we observe here for frequency modulation we have the instantaneous frequency deviation of the carriers. This is proportional again to the message signal d phi over dt kf into mt, so message signal. Or this could be written further that phi t is equal to kf t0 to tt m lambda d lambda, this integral. Once you integrate it, here we find kf is the frequency deviation constant with radians per second per volt, and phi t naught is basically the constant of integration, that phi t naught initial angle, and that has been taken to be 0. So we observed that the modulated waveform xct could be represented as case a cos hc cos omega ct plus kp mt, and this is true for the phase modulation, while AC cos omega ct plus kf minus amplitude m tau d tau, this is for frequency modulation signal. Frequency modulated signal. Now we observe here we have given a corresponding table here. This table is for the type of modulation, whether it's unmodulated, PM phase modulated or frequency modulated, and this is corresponding phase or frequency. What we observe here that phase modulation, the angle varies here, the phase angle varies linearly with the modulating signal here. In frequency modulation, the phase angle varies with the integral of the modulating signal. So we find here, and corresponding you can find the frequency here. This is the frequency for the waveform, that fc you can see here for PM signal frequency is fc plus kp over 2 pi dmt over dt. This is the corresponding frequency, and this is the for FM signal the frequency fc plus kf mt. Now we can see what is the spectra for the frequency modulated signal, because we have more concerned about the spectra to decide on the bandwidth of this kind of modulation schemes. We said angle modulation is non-linear process, so exact description of the arbitrary message is difficult. It's not possible. So if MT is assumed to be sinusoidal, then the spectrum can be obtained. And when we take modulating signal to be sinusoidal, we can analyze the corresponding mathematical equations and get the spectrum. So for MT to be AM cos omega MT, then instantaneous phase division of modulated signal, we can just see here the instantaneous phase division phi t is given by kp AM cos omega MT for frequency modulation, and I say kf AM upon sin omega MT for FM. This we have already seen. For the case of FM signal, frequency modulated signal, the waveform is xt is AC cos omega ct plus beta sin omega mt. This is the corresponding waveform where beta is the modulation index, like kf am over omega m for frequency modulation, and beta p is kp into m for phase modulation. Now to compute the spectrum of XCT, the modulated waveform, what we do it, we can express it into the exponential form. AC, real part of exponential A j omega ct exponential jb j beta sin omega mt, and it can be extended with Fourier series, and we get the following expression for the FM with tone modulation. That tone modulation means single frequency modulation, sinusoidal modulation. And what we observe here, this is the modulated signal we get. This is AC, the constant summation from n minus infinity to infinity, j and beta cos omega ct, omega c plus n omega mt. So this consists of spectrum, consists of carrier components plus infinite number of sideband components, and these components are like fc plus minus n fm, where n is ranging from 1 to 3 and up to infinite. So you get infinite number of frequency components. Here j and beta is the nth order Bessel function of the first kind, and the argument of the Bessel function is beta. Relative amplitude of spectral component depends on j and beta, and relative amplitude of the carrier is written as j0 beta, and large values of beta implies definitely a large bandwidth. When beta is much less than 1, only j0 and j1 are significant. It's like an AM having the carrier plus 2 sidebands, and similar analysis can be done for phase modulated signals. Here we have done for the frequency modulated signal, but it could be done for the phase modulated signal. Now we notice here these two figures here. They indicate that how you could get a FM wave when we have the phase modulated signal. That means if there is a modulating wave, put an integrator, then there is a phase modulator, you get an FM wave, and this is the carrier wave. Similarly, if the frequency modulator is available, you can generate phase modulated wave using this differentiator before the modulating signal. So this is what you could do is it's only block diagram kind of representation. Now we observe here the power and bandwidth for the frequency modulated systems. We observe that a good portion of the total power, like 98%, is confined to some finite bandwidth. So if I take a limited number of side bands, we are not losing much, because most of the power is contained in those side bands. For tone modulation, bandwidth of FM signal is given by bandwidth is equal to twice into beta plus 1 into FM, where beta is delta F over FM. So bandwidth could be written as twice into delta F plus FM. This substitution for bandwidth also is called a Carson's rule. FM bandwidth is twice the sum of the maximum frequency deviation and the bandwidth of message signal. But if beta is much less than 1, typically like 0.3 and less, FM signal called a narrowband FM. When beta is much greater than 1, typically like 5 or 10, FM signal is wideband signal. FM is said to be a wideband signal. Okay, now narrowband FM will describe briefly about the narrowband FM. Narrowband FM is similar to DSP, that means double sideband RAM, bandwidth of NBFM is about twice FM, same as the AM. Narrowband FM, there is no inherent advantage over AM except it uses the UHF frequencies, and it can also work out to be an intermediate step in generation of wideband FM. Narrowband FM is used in mobile communication services such as police wireless, ambulances, taxi cabs, etc. These are the applications of narrowband FM. Wideband FM, here this modulation index much greater than 1. Typically I said 5 or 10. Modulating frequency is from 30 Hz to 15 kHz. You notice here this is for a good music signal. You can get a good music up to say 15 kHz modulating frequency, and maximum frequency deviation here is taken as plus minus 75 kHz, and allowable bandwidth per channel is about 200 kHz. So you notice here the bandwidth is very large as compared to AM systems, and this bandwidth turns out to be about 15 times that of a narrowband FM. So wideband is used in for entertainment type of broadcasting, since the modulating signal bandwidth is very modulating signal frequencies variations are very large, up to 15 kHz. Now we can compare FM with the PM. We can notice here the difference between the frequency modulation and phase modulation. Frequency deviation is proportional to modulating voltage in the case of FM, and phase deviation is proportional to the modulating voltage. Here noise immunity is better than AM and PM. That means FM has a best noise immunity even compared to phase modulation also, and definitely above AM. And noise immunity of phase modulation is better than AM, but not better than FM. It's worse than FM. SNR is better than PM. Signal noise ratio is better than PM, so it's worse than FM. Used for radio broadcasting, used in some mobile systems, and possible to receive FM on PM receivers, phase modulated receivers, and it is also possible here on phase modulated receivers you can get FM broadcast. Now we see comparison of FM and AM. It's very obvious. FM receivers are immune to noise, while AM receivers are not immune to noise. It's possible to decrease noise by increasing the deviation, but there's no such feature is available with the amplitude modulated systems. Bandwidth is higher and depends on the modulation index. Here in the frequency modulation, bandwidth is lower than FM and independent of the modulation index. FM transmission and reception equipments are more complex here. These are simple, and all transmitted power is useful here. Carrier power and one sideband power is useless in the case of amplitude modulated systems. Now we'll talk very briefly about the generation of FM waves. There are two methods available, like one is direct method that requires VCO and provides frequency deviation. Carrier frequency needs to be stabilized here. The circuits use are reactance modulator circuit or varactor diode modulator circuit. Indirect method is a frequency up conversion using heterodyning method or multiplication method. The most popular method is the Armstrong modulator. And you can refer to any book, standard book, you will find the details of this, because not much related matter appears in the problems of gates, so this portion has been very briefly discussed here. FM detection, we get to back original modulating signal we have to get, and it is achieved by converting frequency deviation of FM signal to the variations of equivalent voltage. That frequency deviation, that may changes in frequency, is converted into the voltage change such circuits called frequency discriminator, and message signal recovered from the AM signal by envelope detector. Now you can, after that you can use envelope detector. Most common demodulator is a PLL demodulator. This, for the frequency demodulation, phase lock loop demodulators are very common and used for both narrowband and wideband modulating, narrowband and wideband systems. This is probably the last slide here. This gives an advantage of FM and disadvantage of FM. By now you must have known obvious that amplitude of FM wave remains unaffected, because once the FM wave is modulated, when the carrier is modulated by FM, then its amplitude is not changing. So it's a great advantage because the noise will not be added. Decrease in noise, hence larger SYN, because it gives lower noise here, so SYN would be larger. The comparison of signal to noise ratios for all modulating schemes, AM or FM or phase modulation, we'll be talking in the third part of the video, which will be after this. Now noise reduces by increasing deviation. This is very obvious. That means there is the adjustment available. That means if you want to reduce the noise, you can increase the deviation. Increasing the deviation will mean we take large bandwidth, but that is a sacrifice you have to pay for it. Disadvantage of FM wave cannot cover larger areas, because FM waves are operating at like VHF and UHF frequencies, so they cannot cover large distances, like maybe 50-60 kilometers, an ideal distance. Transmitting and receiving equipments of FM are complex and costly, and the last point is much wider channel bandwidth is needed here, that is 200 kilohertz is needed for FM, while you have noticed that in AM you need it hardly about 10 kilohertz, even if you transmit both the sidebands. Otherwise, if you transmit with single sideband, it's only 5 kilohertz. So that way you need a much larger bandwidth in the case of frequency modulated systems. Okay, that is all I wanted to tell you about this. So this is the second part of the video. It's on angle modulation, and third part we'll talk about the noise in the amplitude modulated system as well as angle modulated systems, and we'll quite briefly try to summarize those observations, since there is not much details are being there in your gate problems regarding signal to noise ratio of these modulated waveforms, but still we'll try to touch them and tell you about what are the important noise parameters, signal to noise ratio. And this noise is not helpful only for the analog modulation schemes. This noise concept also goes to our digital modulation schemes, where we define this in terms of the bit error rate. Okay, happy viewing. Thank you very much.